Everyone. This lecture is on first order systems in series continuation part 3. There were two parts earlier. In those we have seen what are the meaning of first order systems in series, how can they be connected, and then we saw in detail about non-interacting systems. Now in this lecture we will be seeing in detail about interacting systems. First we will see how to write the transfer function of interacting systems. So let us take any two first order systems connected in an interacting manner. This is just a flow sheet where two first order systems are connected and they are interacting. Okay, and they are interacting. So these two first order systems in series are interacting systems. Let's see how do you write the transfer function of this. So now, unlike non-interacting systems where the overall transfer function is simply the product, but in this case the overall transfer function is given by this equation. So if you compare this with the overall transfer function of two non-interacting systems in series, you find that there is an extra term C1R2S in the denominator. So this can be considered, up to this it can be considered just the product of the two transfer functions, but there is an extra term which is C1R2S. There is an extra term C1R2S. So in this, so the overall transfer function x2 by x0 s is given by this k1 k2 divided by tau1 s plus 1 into tau2 s plus 1 plus c1 r2s, where c1 stands for the capacitance of the first system and R2 stands for the resistance of the second system. So every first order system has got a capacitance and a resistance. So C1 is a capacitance of the first, R2 is a resistance of the second. So in the denominator of the transfer function there is an extra term C1 R2S. So this extra term comes because of this interaction between these two tanks. And this term is also known as loading or interacting. This term comes because of interaction between these two, or it's also known as loading. So this presence of this extra term is going to change the dynamics of non-interacting systems as compared to, this extra term C1R2S, the presence of this extra term C1R2S, the denominator, is going to change the dynamics of interacting systems as compared to the response of the non-interacting systems. Okay, so let us see what will be the response of this for a step input here and see how does it behave. So before that, for that, let us take the usual example of two tanks in series. So we'll take the example of two tanks, interacting tanks in series. So this is a figure for two interacting tanks. Only the subscripts are missing. This is H2. Okay, this is H2. This height is H2, and this is Q2. This is Q1 here. Subscripts are not properly mentioned. So this is Q1, this is Q, this is H1. Okay. So, and this is the this is two interacting tanks in series with the usual notation. Now if you see the transfer function of this using the previous formula is H2S by QS equal to R2 by the 2 time constant tau ns plus 1 into tau 2s plus 1 plus A1 R2S. So the capacitance we have seen earlier, the general formula I told you, C1 R2S. Okay, so this I told you is C1 R2S, but C1 is capacitance. Capacitance for the first tank is here C1, C1 C1 is nothing but area. A1 is area of the first tank. R2 is resistance for the second tank, that is the resistance of the second tank. So the capacitance of the first tank is area of the first tank. By the way, this equation is not a assumption. This can be derived. This is a derived equation. This overall transfer function of these two interacting tanks as given by this equation can be derived. This can be derived. Well, so H2S by QS, H2 is this, okay, H2, and this is Q, H1, and this is Q. This Q is input to the flow input to the first tank. H2 is the height of the liquid in the second tank, and you have to remember that all these variables are in terms of the deviation variables. Okay, this is not here it is shown as small h2. If you are wondering, here is shown as small h2, small case, here is uppercase capital H2. So that's the usual notation, and you know where that, for example, let me tell you, capital H2 means H2 minus H2S, all deviation variables. Okay, similarly Q, so all these capital letters are deviation variables. Now this denominator can be split into two effective first order terms. This denominator can be split into two effective first order terms. So this is this three terms, two product of two terms plus another term. The whole denominator can be split into two terms, tau a s plus 1 into tau b s plus 1. Where this tau a and tau b are called effective time constants. So tau a and tau b are called effective time constants. So they are not the same as tau 1 and tau 2. Tau 1 and tau 2 are the actual time constants of the two systems. Tau 1 is the time constant of the first tank. Tau 2 is the time constant of the second tank. The actual time constants. Whereas tau A and tau B, they will be different from tau 1 and tau 2. They are known as effective time constants. They are different. Their tau A and tau B are different. In fact, one of the time constants, one of these say tau A will be greater than tau 1 and tau 2. So tau B, another time constant, tau B will be less than tau 1 and tau 2. So it doesn't matter which is tau A, which is tau B. One of these time constants, let's say tau A will be larger than tau 1 and tau 2, and tau B will be less than tau 1 and tau 2. So this means the effect of this interaction is to change the effective time constants of the system. So this term and this term are same, exactly same, but only thing tau A and tau B are different, as shown here. One of these tau A will be much greater than tau 1 and tau 2. Other constant tau B will be less than tau 1 and tau 2. So this interaction, what does it do? It has changed the effective time constants, and since since tau A is greater than tau 1 and tau 2, this implies that the response of these two interacting tanks is going to be slower than the response compared to non-interacting tanks. So the response of the interacting tanks or general interacting systems will be more sluggish compared to the response of non-interacting systems. That is because of this interaction, which mathematically comes because of this additional term a1 r2s or c1 r2s in the denominator of the transfer function, which means the actual time constants are changed into two effective time constants which are different from the actual ones. Sorry, this is and, not infinity. This is not infinity, this is and tau B less than tau 1 and tau 2. Okay, so that much about this overall transfer function of two interacting systems in series. Now let us overall transfer function. Let us find out the response of this for a step input. We'll give a step input here, Q, that is inlet to the flow rate, and as a result, this is the input. We'll find out how the level in the second tank changes by giving a repeat. We'll give a step input to the inlet flow rate, Q, and we will find out how does this level H2 change. So this is the step input, step input to the inlet flow of the first tank, Qt equal to m into ut. M is a magnitude. As usual, take the Laplace. Q of s equal to m by s. Substitute in the transfer function. So H2s equal to qs into gs. That is this m by s into this. Now if you take the inverse of this, Laplace inverse, you are going to get the response equation. Okay, Laplace inverse of this term. So Laplace inverse of this term is m is a constant, r2 is a constant, remaining terms Laplace inverse is this, right? Now so it is looks similar to the response equation of the non-interacting tanks, but what you have to pay attention is these are not the actual time constants, they are the effective time constants. Okay, these are the effective time constants, not actual time constants. So if you make a plot of this, how does it graphically? Let us see visually how this equation compares with the equation of non-interacting systems in series. So the So this is a step response of interacting systems. Okay, just shown just now. This is that response, that equation, this equation. If you plot this equation, it will look like this. If you on the same graph, if you plot, suppose these two tanks, had these two tanks been non-interacting, how will the response show up? So that is the upper curve. So what do you find in both? So I have shown for step response of two first order systems in series, not necessarily tanks, general systems. If you write specifically for tanks, what is shown here is this is yt by mk. This k has come out here. This should be yt divided by mk. The x-axis, y-axis is y by mk. So m is in the denominator, both m and k are in the denominator. It is shifted in the presentation. So the y-axis is y by mk. Okay. Now if you specifically plot for two tanks, then this y-axis will be h2, response is h2, by k is r2. So if you plot for two tanks, specifically for tanks h2 by mr2, in general, by general notation I have shown it as y by mk. So for non-interacting, this is the response equation, upper one. For interacting, this equation. So what does it show? The response of interacting systems becomes slower than non-interacting response of non-interacting systems. That means because of the interaction, the response becomes more sluggish. And also there is a transfer lag which we have discussed in the last part. So the transfer lag exists both for non-interacting as well as interacting systems. That is, the response does not begin immediately at t equal to 0. Does not immediately begin at t equal to 0 because the slope of the equation here, because the slope of the equation at t equal to 0 or the origin will be 0 here. Okay. So there the transfer lag exists at both places. For both cases, transfer lag exists for both cases, and transfer lag will be more for interacting systems than for non-interacting. Okay, right. So that much for the transfer function, overall transfer function of interacting tanks or interacting systems compared with non-interacting systems. Okay. Now I'll show you something more interesting. Okay, 1 minute. Now I'll show you the exact comparison done practically. That is the step response of interacting tanks comparison with what this graph is going to show you is comparison of experimental values with theoretical values. So two interacting tanks as shown in the previous figure. That was given a step input, the inlet flow rate to the first tank, and the height of the second tank is measured, and the actual height, small h, after the deviation variable, the exact height, small h, is calculated, and the experimental values are plotted. That is the first top curve, experimental values, experimentally done. It's compared with the theoretical values. Theoretical values means that calculated by the previous equation, what we derived just now. That is this equation. So this will give you capital H2T, and from capital H2T you can find small h2. This is a deviation variable. You can find the actual height small h2 by the equation I shown earlier, because capital H2 equal to small h2 minus small h2s, steady state value, yes. So from that, actual height can be found. So this is the theoretical curve. The values of this equation is plotted by the, as per the values given by this equation. And the top one, upper one is actual experimental values. So you see both agree qualitatively, even though quantitatively there's small difference, which may be, I don't want to go into the details of the reasons for the error. There may be there's some error because of experimental methods, experimental error, the reading error, etc. But qualitatively both agree with each other. The theoretical values plotted in this graph plotted as per the theoretical values, and upper one the actual values actually done experimentally and measured. So the theoretical equation shows a transfer lag here, but you may be wondering, but the transfer lag does not show up in the experimental values. So that is because this transfer lag will be visible very close to the origin. So this is in terms of seconds, actually plotted in terms of seconds. This is 5 seconds. So very close to the origin. Maybe if you measure the height at 1 second, or even better at 0.5 second, 1 second, if I measured the rate, measure the height at 0.5 second, 1 second, etc. and plotted, then the transfer lag would have been visible even in the experimental values. But practically it was not possible to measure the height 0.5 seconds after the disturbance or 1 second after the disturbance. I think the first value was recorded at 5 seconds after the disturbance. That is the earliest time you could measure the height after giving the disturbance. That's why the transfer lag is not able to show up in this. Actually, this portion is not exactly correct experimental values. They just plotted. It starts from this 5 seconds. So the point I want to make is experimentally the system behaves as calculated by as given by the theoretical equation. Both agree qualitatively the nature of the graph. So that completes first order systems in series, this 3-part lecture. The first order systems in series are important because often systems can be considered to be 2 or more first order systems in series. So a system may have a complex transfer function, but practically if you see with some approximation or even with the exact value, it can be considered as 2 or more first order systems in series. So that will make our analysis of control systems simpler. So that is why this first order systems in series was discussed in detail. So that is the importance of first order system series, how it can be, and how do you find the response equation, how do you write the transfer function, then how do you find the response, how do the responses of each behave compared to single system, and how non-interacting response compares with response of interacting systems. So that completes this chapter topic, first order system series. So if you have any question, if you have any comments, you can leave it in the section. Please share this to your friends, to other students, to anybody. Okay, that's it. Goodbye. Thank you and goodbye. Till next we see you.